Okay, so in this video, we're going to talk about exponential functions. So the first thing you need to remember is the formula for compound interest, which is right there on your notes. You just want to remember that A is the amount that's in the account. B is the principal, or the amount you put in the account to start with. Missed an I in there. And R is the rate in a decimal. Okay, so if it's like 10%, you put 0.1. And N is the number of times it's compounded. All right. So, for example, how much is in an account set up with $2,000 when my 3-year-old was born if it is compounded annually at a 5.5% interest rate? How much is in the account when she turns 18? Okay, so there's two parts to that problem. First of all, we don't know the amount in either case, but we know that $2,000 is the principal. Okay, we know we do 1 plus the interest rate, which is 0.055. Okay, and then we're doing it to the third power for 3 years. All right, so we do that. I got $2,348.48. Remember, only 2 decimal places for money. It's silly to go past that. Now, what about when she's 18? Everything's the same except that now you're going to go for 18 years. So that third power is really 18. Okay. Now, I'm not putting the times 1 and the divide by 1 because compounded annually, that n equals 1. So if I put in the n equals 1, you'll see it's the same. All right, so when I put those in, I got 5,242.93. You go ahead and try the same thing for my twins, but this time it's compounded monthly. So that means the n equals 12. See how that changes it? You do it, and I'll show you what I get. Pause and try it. Okay, and so this is the answer I get when I do both of those. Notice the only thing that changed is I had to add that n is 12. I'm compounding it once a month, so 12 times a year, so I have to add that in. So notice that it is better to get interest more often. Okay, each time it was just a little bit more. Now, exponential functions, they always look like f of x equals a to the x, where a does not equal 1. Okay, they might have a leading coefficient that will make it bigger and smaller, and they might have add 1 to the x to shift it to the left or subtract to shift it to the right, or they might have add 5 to the whole thing and then I'll shift it up and down, just like any other function. That a is called the base, the x is called the exponent. All right, so I want you to go ahead and graph each of these and see how they are different. So the only things that's different is the base 2, 3, and 5. Okay, so I've drawn all them in. Notice I color-coded them. 5 to the x is blue, 3 to the x is red, and 2 to the x is black. Notice that over here that once you are talking about x as being positive, it has 5 to the x is bigger, 2 to the x is the smallest, 3x is in the middle. However, when x is negative, okay, so we're talking about negative exponents, the bigger the base, the smaller it is, because think about it, we're doing 5 to the negative 1 or 1/5 versus 2 to the negative 1 or 1/2. So they are all the same in that they all have the same y-intercept of y equals 1. Because, remember your exponential rules, anything to the 0 power, if we're putting x equals 0 in, is 1. Same thing with 5, it's 1. So they all have the same x-intercept. All right, so state the transformations and use them to graph. So our parent function is y equals 3 to the x. Okay, this 2 here is going to stretch by a factor of 2. okay? And that minus 4, since it's outside of the function, it's going to make us go down 4. Okay, so those are our shifts. So let's talk about what the original function is. This is not the one they're asking us to graph. The original function, our parent function, would have a y-intercept at 1, and then the next point at 1 comma 3. This is just a sketch, and it does have asymptotic behavior here at 0, which I don't think I mentioned in the last slide. So if you noticed there were asymptotes, there were. All right, so now let's use that to do our shifts. So if I stretch by 2, I'm going to change to red. If I stretch by 2, that means that I'm up here at 2, and then I'm up at 6. 6. All right, then I'm going to be at like 2/3 instead of 1/3. All right, so I'm sketching. All right, now that whole thing has to shift down. So I haven't done that part, so I have to shift down. So my real graph is going to look like, here we go, from 6 down 4, I'm going to be at 2. And my asymptote, instead of at 0, is going to be shifted down by 4 also. So my asymptote is going to be here. And voila. It's a sketch. It's not perfect, but it's a sketch. So those first two are just to get our bearings. That last bigger one is it. So state the domain. The domain is all real numbers. Okay, if you really want to use interval notation, negative infinity to infinity. All right, and our range is everything above negative 4. So you could say y is greater than negative 4. Since I'm trying to use interval notation, I'm going to do negative 4 to positive infinity. All right, find the zeros graphically. All right, we're going to use our graphing calculator to find that. So go ahead and type it in your graphing calculator if you haven't already, because that might have been how you found it. You have two options. You can either go ahead and go second trace, that's calculate, and find the second choice is calculate as 0. And then you just have to make sure you select a range kind of in between there so that it can find that 0. And then find it. I got x equals 0.630, okay, or 631 if you want to round properly. In AP, you can either round or truncate. Truncate means just cut it off. Doesn't matter. They don't care. All right. The other way to do it is to also graph y equals 0 and then find the intersection. So I'll let you remember how to do that. If you need to ask me in class, you can do that. And there you have it. So this is the 0. It's just another word for x-intercept. So 0.630, comma 0 if you want to write it in a coordinate pair. All right, so how do you find the zeros algebraically? Remember, that's where y equals 0. So in other words, how do you solve that? First things first, you need to add 4 to both sides. Okay, then divide both sides by 2. Okay, so to get rid of this, I personally take the log of both sides. Okay, now in calculus, we take the natural log most usually, but remember there's that x as an exponent, and the rule is when you have that, you can bring it down for logs. When you have an exponent inside of a log, you can bring it down. So now we have x equals, if I divide both sides by a natural log of 3, or if you want to use log base 10, that's fine, but usually in calculus we use natural logs. And then you can get that right on your calculator. This is an exact answer, but as we got before, it should be 0.630. There you go. All right, so don't forget your exponent rules. Okay, if you have a to the x times a to the y, that's a to the x plus y. So like if you have x squared and x to the third, that's x to the fifth, for example. All right, or if you have 3 to the 2 and 3 to the 8, that's 3 to the 10th. You add the exponents. All right, so similarly, that's x minus y for when we have division. Now, if you have a power raised to a power, you multiply the exponents. Okay, so like if you have x times, or x squared to the third, I'm getting too many parentheses, I'm sorry if that's a little annoying, but you multiply the exponents. X to the 6th. So the next one, if you have different bases but the same exponents, really that is the same thing as saying AB to the x. So for instance, like if you have x to the third and y to the third, that's really xy all to the third power. Similar idea. All right, and don't forget if you have parentheses, that parentheses goes for both. Kind of the same idea as what we were saying here. Same deal with parentheses on division. It would be a to the x and b to the x. All right. So if I got this example here, this is like the first one. So we have 2x plus 3, because when you have the same base and different exponents, you add the exponents. When I have the same base of 4 and I have exponents, I can subtract the exponents if I'm dividing. If I have something in parentheses, all raised to the power, you multiply the exponents. So 2x. 2 times x is 2x. We have different bases, and I'm raising them both to the same power. That's really both things all raised to the x power, or in this case, just 21 to the x power. And the last one, that x goes to both. Okay? And that's all. You can't simplify it anymore. All right, so half-life. Radioactive decay is an example of exponential decay. Okay? So exponential decay. I'm abbreviating. All right. Meaning that it follows this formula, a to the x, okay, with some constant out in front, might be 1. So f of x equals k times a to the x, where a is between 0 and 1. So in other words, it's some kind of decimal between 0, or fraction between 0 and 1, like 0.25. Okay? Exponential growth, it follows the very similar formula, but the a is bigger than 1. It might be 2.5, it might be 1.3, but it's causing it to grow. Okay, so half-life is the time it takes for half of the initial amount to disappear or decay. Okay, half of the initial amount to disappear or decay. All right, so how do we answer this example where the half-life for a certain radioactive substance is 20 days and there are 5 grams initially? When will there only be 1 gram remaining? All right, so okay, so we have f of x equals a dx, and I forgot my k out in front, okay? So that k is like the principal or the original amount. That a is like the 1 plus r. Actually, we're going to talk about 1 minus r since we're decaying. We're subtracting percents off, or subtracting or decreasing by a rate. And that f of x out front is like the amount that's in the account, but it's the amount of substance there is at the moment. So it's a half-life for the radioactive substance is 20 days. And so if they're initially 5 grams, that's your principal. We don't know the rate at which it's growing. The x is the time, the 20 days. I shouldn't put the x in. 20 days. And in 20 days, if we started with 5 grams and 20 days gives us a half of that, it should be at 2.5 grams at that time. So to solve this equation where you have, I'm going to put parentheses there so it looks a little better, I need to divide both sides by 5 because it's multiplying by 5 on this side. So if I divide by 5, I get 1/2 equals a to the 20th. And to get my a, I need to 20th root both sides, or take it to the 1/20th power, whichever. I'm writing 30 even though I said 20. Okay, 20th root of both sides, and you can do that in your calculator. Or you can 1/20th, take it to the 1/20th power, that also works. So either way, we get a equals 0.966, Always take it to 3 decimal places for AP. That's their rule. All right, so 0.866, 0.966, and that's our growth rate. And remember, that's like our 1 minus r. So if we actually want to figure out what the rate at which it is decaying, you have to do 1 minus 0.66, and you get like about 0.4, right? So about 0.044% is what you're decaying at. That's the rate. All right. So that's not what they asked. It said, when will there be only 1 gram remaining? So part 2 of this is to go back to your equation and say, okay, I know my A, I know my K, my initial amount, I know my rate, my 0.966, or that it's decaying at about 4%-ish, I'm rounding, and that we will have 1 gram remaining, so that's our f of x part. So we have 1 equals, and then our P or our K, our initial amount is 5. We figured out our A has to be 0.966, and we don't know how much time it's going to take to the x power, or t if it makes you happy to change that. So now we have to solve that. All right, so if you solve that, you got to divide by 5, so you get 0.2 equals 0.966 to the x power. Now to get an variable out of an exponent, you do need to take a log of both sides. I do natural log because that's what you do in calculus more often than not. So I'm going to do that. And so when I take the natural log, I can bring that exponent down in front of a log. So it makes that exponent that variable peel out of the exponent. Okay, so then I've got this equation, and now to get the x by itself, just divide both sides by natural log of 0.966. All right, so both sides, 6. All right, so in other words, you get, these cancel, okay, you get x equals whatever the natural log of 0.2 over the natural log of 0.966 is, and you can do that right in your calculator. If you do that in your calculator, you should get the x is about 46.388 days. All right, so a little over 46 days. Somewhere on the 46th day, but before the 47th day, there will be only 1 gram remaining. So exponential regression, there is a table here. I want you to enter it into your calculator, just like you would as if it's linear regression. Now, you're going to put this in L1, L2, and stat, enter, okay? Kind of put some instructions on how to do that right here, okay? Some reminders. So stat, edit, enter the data into L1 and L2, and then go to y equals to turn on the scatter plot. Make sure when you do your stat calculate that it looks like this, and then your scatter plot will have that in here. Here's what your equation should look like. If you look at those little pluses, those are the points for my data, and it looks like an exponential, and since we're studying exponentials, lo and behold, I used an exponential regression, okay? So I use exponential regression in this one, not logarithmic, not quadratic, so I use exponential regression. So after I did that, I got the equation y equals 56.469 times 1.151 all to the x power. All right, so I'm using 3 decimal places because that's AP's rule. I truncated because I was being lazy about my 5 afterwards, not rounding it up to 70, to be honest with you. So that's my equation, and I'm going to use it in the next part, so I'm going to transfer that. One thing that I forgot to mention is kind of important. I used, for my x1, I went ahead and made that 0, then 1, then 2, then 3, then 4, all the way down to 11, so that I didn't have these crazy big numbers to type in and these crazy big numbers on my stat plot. So see, they're not so, my x's aren't way out at 2,000. All right, so when I'm looking for my next problem on the next page, when I'm talking about the year 2000, I'm really talking about when x equals 12. All right, so I am going to go ahead and use this equation that we had from the former up above for you. And we're going to predict it. Remember, x equals 12 for the year 2000 because we didn't start at 0. So if I put it in, I'm sorry, my handwriting is so deplorable on this sometimes. It's really difficult to write on a screen with a stylus. I am learning something new about myself. All right, so there you have it. And if you calculate that, you get 308 plus 261 million people. All right, so the actual data it says is 281.4 million. So you can see this is actually a lot bigger, actually about 9.5% bigger if you do a little math out, if you do a little math there. But so it, just because you have an exponential equation, it looks pretty good. It doesn't mean that it's perfect. It is an estimate. It is only approximating where you might be, but it's only a prediction, and it's not necessarily the end-all be-all. All right, so the second part, use exponential equation to determine an approximate annual growth rate. Well, remember that this is our A, which is really the 1 plus R, tells us the rate. But our rate is in 10-year increments. So since it was in 10-year increments, we're really talking about this to the 10th power is equal to 1.1519. Just like in our formula, we were 10 years, so the time part goes up here. So the whole thing gave me this part for my A, my growth rate for that 10 years. All right, so if we have to solve for R to figure out the growth rate, we have to do the 10th root of both sides of this. So if you do the 10th root, I'll let you do that in your calculator, but you should get the 10th root of both sides. And I'm going to do it all at once as I write it down here. I don't know why I did 4 decimal places. And then I'm going to subtract the 1 off also, because now I have to subtract 1. So whatever the 10th root of all that is. Okay, if I do that whole thing in my calculator, I get 0.014. So about 1.4% is about the annual growth rate, approximate. Now, E. E is a number. Okay, natural log uses E. Okay, natural log is the same thing as log with a base of E, if you can remember. We'll talk more about logs later. But continuous compounding is the same as our normal compounding, except we've got our rate up here. So we've got our principal. We're doing our base is E, and it's multiplied by a rate, so it's E. It's continual growth, like every minute of every second of every day. It is exponential growth. Why? Because that A, our E, happens to be bigger than 1. And when the A, the base, is bigger than 1, it is growing. All right, so what if I use that same example we started out the whole thing with about the $2,000 for my twins, but this time I'm going to compound it continually, which is impossible, but, you know, whatever, if we could, at 5.5%. Okay, we're going to do it when they're 3 and when they're 18 again. So again, we're going to have y equals our principal, E to the rate. Remember to switch it to a decimal correctly, 0.055, and to the time. And you're going to get an answer. Okay, so I got 2,358.79. And if I wait till they're 18, same deal, except 18 years, I got 5,382.47, so 47 cents. If you compare those to our original two when we compounded for Alyssa, she had less because she was compounded annually than the twins who are compounded monthly, and then the twins, if they're compounded continually, they get even more. So the more you compound, the better you're off. All right, and that sums up what we were going to talk about with exponentials. Come to class with questions.